Hello, in this video we're going to look at the mean and variance of a folded normal distribution, and we're actually going to derive the PDF of it also. So let's jump right in, and y is called a folded normal distribution if it's the absolute value of x, where x is a normal distribution with mean, mu, and variance sigma squared. Or it's often written like this, that y is equal to the absolute value of mu plus sigma z, where z is a standard normal. And again, y is the folded normal distribution. Pictorially, it looks like this, that if we have a normal distribution here, so that would be our x, and then we take the absolute value of it, so this piece here gets folded to the positive piece, but this and this are added, so the folded normal distribution looks like this. Now, the normal distribution, okay, with any mean can be anywhere along here, so basically what happens is the negative parts of it are folded back to the positive, and they're added to have one distribution. So first, let's derive the distribution, and note that y equals absolute value of x is not a one-to-one function. And so whenever you're doing a transformation, you have to break it up into regions that are one-to-one. So if, if this is x down here and this is y axis, the abscissa and the ordinate, or the x and y, if we break it up into, say, region 1, then this little piece is a one-to-one function. It passes the vertical pencil test, only hits it once. It actually passes the horizontal pencil test, it only hits it once in this region. And then we'll call this region 2, and it's also a one-to-one function of this. So we have to do it in piecemeal, or over each region, then add them together. So in region 1, x is just x because they're positive, and the Jacobian would be 1. And over region 2, it's y equals minus x, because since these are negatives, you have to take the negative and make it positive, and that's what the original function says. And so here, again, the Jacobian is 1. When you back solve for x, you just get x equal y, and here you get x equal minus y, and this will play a part in a second. So the function, just looking at this piece here, so f of y is f of y1, over region 1, where you plug in x here into here. Now, technically, I should say times the absolute value of the Jacobian, which is 1, but I forgot to write it, but it doesn't matter. And then this is over region 2, so we add it over the function over region 2. And so it's f of y2 of x, but it's this x, so it's minus y. And since x is normal distribution, we plug in this into our normal distribution, which is this, so the y goes there, otherwise it's a standard normal. And here we plug in x, plus, that plus, but we plug in x is equal to minus y. Now this is a little tricky here. It's the standard normal, e to the minus, and then you have the 2 sigma squared here. And technically you stick in a minus y, right here, minus y minus mu. But the minus can be brought out into minus 1 squared, which is 1, and yet it's left with y plus mu. So this is the density, and we're actually finished. But some go further, and so let's go farther to match what is sometimes reported in the literature. So we have some commonalities here. We can factor out this, factor out that, and here when we expand the quadratic, we have y squared minus 2y mu plus mu squared. And here we have y squared plus 2y mu plus mu squared. So we have some common factors, and the common factors are the y squared and the mu squared. So we factor those out, and then what's left is, I guess technically this piece is this one, So no, it's not. Dang it. So the minus goes into the minus. And we get 2y mu over 2 sigma squared. And those 2's will cancel. And then here that minus goes into the 2y mu and makes it a minus. And again, those 2's will cancel. Well, this sort of looks like the hyperbolic cosine function. If we could divide by 2, but then we'd have to multiply by 2, this is the hyperbolic cosine function. And so that's what they do. So we have a mu y over sigma squared minus mu y over sigma squared, divide by 2, and we get this. But since we divided by 2, we have to multiply by 2, and the 2's kind of cancel out each other, and we get this. And so this is also the density that's reported in the literature. Both are used. So let's jump right into the mean. So the mean of y is the mean of the absolute value of this quantity. Okay, but let's break this up and create like indicator functions where this is positive and where this is negative. So we do it on both. And so this is the expected value of mu plus sigma squared such that this is positive plus, and actually this is a comma. And so I almost thought about writing it as an indicator function. So it's this times the indicator function where this is positive. And I think they're the same, but I wrote it like this. So, and then where this is negative, you take the negative of it and it makes it positive. Where this, this such that this is negative. Okay. Well, let's do this then. So if we factor out a minus to both of those and make that a minus, so it'd be the expected value of mu plus sigma squared z. Okay, but that's a minus. So now if we subtract that again from both sides, okay, so here that we add a mu plus sigma squared such that this is negative, and then we do it again, then this side just becomes the mean of mu plus sigma z. So that's what this side, we subtracted it, and then let me rephrase that. We added it and then we subtracted it, and that's why we get 2 of these over here. And that step is crucial. And so we're here, so we factor out a minus, then we take this piece, which now is mu plus sigma z, we add it and then subtract it. But one of those can be added to this, which makes it this, and the other, the subtracted piece, is subtracted again, which makes it 2 of them, and so we get this. Then over here, we have the expected value of mu, and then z times expected value of z, which is 0 because it's a standard normal. And then over here, we have a constant, so it's minus 2 mu such that z is less than this quantity. Oh, and from here, that's equivalent to z being less than minus mu over sigma. Okay, so then we take the mu down, and then over here we have the minus 2 expected value is sigma z such that z is less than minus mu over sigma. Now over here, this is like an indicator function. So it's 0 if z is not less than this. So if z is greater than or equal to this, it's 0. If z is less than this, then we look at this quantity, the expected value of mu. So it's like an indicator function. So the expected value of mu is actually mu times the probability of this happening, which is what this says. So it's minus mu times the probability of this, but this is a standard normal, so it's phi of minus mu over sigma. So that's what this quantity equals. Now this quantity, the sigma's constant so we can bring it out, but then it's the expected value of this. And so somehow we're going to have to figure out what this is. And so let's do it. So let's look at this expected value by itself. And that's what this is. So that says integrate, take the, it's z times this probability over the range of this, which is what this says. Now let's do a u substitution of z squared over 2, and you get du equal to z dz. So substitute that in, we get this. So the u here, that z goes in with this z, and we're left with this. So then this becomes a constant that can be factored out, and you have the integral of e to the minus mu, which then is minus e to the minus u, and then we have our constant out front, integrated at these limits. This says plug it in, and then when it's infinity, it goes to 0, so we're left with just this piece here. So now we know what that expected value is, which is this. We can plug it in for this piece here. So that tells us that expected value of y is equal to mu minus this piece here plus sigma times this piece. Well, it's actually minus, so it becomes a plus times this piece, and that's it. And we call that the mean of y. And then so we're finished. That's the answer. Now, to look at the second moment, the y squared is equal to the absolute value of y, or x squared, which then you can take away the absolute value. But the expected value of x squared is equal to the variance plus the mean squared. Well, that's equal to sigma squared mu squared. Okay? So now once we know the expected value of y and the expected value of y squared, we can find the variance because it's this formula here. Well, the expected value of y squared, we said, was sigma squared plus mu squared minus the mean of y squared, which we said was this piece. And so we're finished, and that's the answer. So that's the mean and the variance of a folded normal distribution. So I hope you enjoyed it. I did. Please like it if you did, and subscribe so you don't miss the next one. Thanks. Bye.